All right. So a lot of you probably are wondering why we have been why have been forced to take this course while we are here to do engineering, electrical engineering, computer science, chemistry, biology, or maths. Why do we need to do physics? So and that's a fair concern. What I want to just say is that all these disciplines, biology, computer science, uh, and electrical engineering, all the science and engineering disciplines have become increasingly interdisciplinary. So knowing another area, another allied discipline, for example, physics, if you're going to do chemistry, or chemistry if you're going to do biology, or if you're going to do computer science, they are a great asset. Engineering has always been very quantitative by nature, but there are other disciplines, for example, which are not known to be very quantitative. For example, biology is not known to be very quantitative. You don't have a lot of equations, you don't have a lot of mathematics. But let me surprise you that biology have become more recently very quantitative. For example, molecular biology is very quantitative. The other computational biology, for example, proteomics, there are a lot of sub areas in biology which have become very quantitative. And through this course, as Dr. Adam mentioned in one of his emails, we are going to learn how to apply mathematics, how to mathematize natural phenomena, how to apply mathematics and learn natural laws, code natural laws or observation in terms of equations. And this is a great asset. Doesn't matter which discipline later you're going to choose. And one more thing, for example, about yeah, I think that's it that I wanted to say about why we are doing mechanics or why we are doing physics. So although the course is mainly about physics, the first few lectures would be on calculus, where we would be learning some basic concepts of mathematics that we are going to apply. And the two most important concepts that we are going to learn is derivative and integral, right? Today, we are going to focus on derivative, and to understand this mathematical concept, we will use again a physical phenomena that and then we will develop the mathematics of that phenomena, and then we try to learn the concept of derivative along the way. And I'm going to use an example. I'm going to use an example from physics, which you're all too well familiar. Motion under free fall. What is motion under free fall? Well, this is motion under free fall. When you drop an object from a certain height above the surface of Earth, and as it drops freely towards Earth, that is motion under free fall. Let's say this is an object, and here is the surface of Earth, right? Now, as we hold this object, its position or the distance it has traveled is 0. I denote its position with x, and that is 0. So is its speed. To keep the discussion simpler for the time being, I'm just using the speed. If you're wondering why I'm not using the word velocity just yet, we would be dealing with velocity later on. Now, if you take this object to certain height and then release it, then it's going to hit the surface of Earth after certain time. And this is motion under free fall. And Galileo was the first one to look at it and do experiments with it. And Galileo demonstrated that regardless of how heavy the object is, heavier and lighter objects fall at the same rate. The fall rate for the heavier and lighter objects is same. What we mean by fall rate, well, we will define a concept if you haven't already guessed, but a more simpler answer is that a heavy object and a light object, when they fall from the same height, they take the same amount of time to reach the surface of Earth. And this may be a little bit counterintuitive to our everyday observations. For example, if you drop a feather and a chalk, for example, the chalk would fall faster and reach the surface of Earth before the feather does. But because Galileo's observation was assuming that the objects that he was considering they were chosen in such a way that the air resistance had minimal effect on the objects, or the experiment, or if you perform the experiment in vacuum. There is a YouTube link in one of the at somewhere in the first chapter of your notes. You're free to watch. There's a very nice demonstration of falling feathers and heavier objects in vacuum. But if you want to do little experiment here, for example, I have these two pieces of chalk. You see this? This smaller piece is probably 1/4 the bigger chalk. And if I drop them together, well, you can't see the surface here, but well, take my word for it. If I drop them together, they arrive the surface of Earth at the same time, because chalk is such an object where air resistance has very minimal role. And that's what Galileo had demonstrated. The fall rate is independent of the mass or the weight. Weight is, I use in the more common sense the word weight, because weight is, so I don't want to confuse you. Let's say lighter and heavier objects for now. So Galileo said that fall rate, he demonstrated that the fall rate for heavier and lighter objects is the same. Well, there's more. If you ignore the air resistance, if the air resistance is present, then this statement doesn't hold. But we are assuming ideal conditions. We are assuming for this example, we are assuming that there is no air resistance. All right. Now, this is all very well, that we have learned a new principle that heavier and lighter objects fall at the same rate. But let's say somebody asks you this question: how long? Let's say you drop this object from 100 meters height. All right. Now the question is how long it takes, or let's say the other way around. How much this object travels in 2 seconds. So there is another variable here, time. So of course, initially everything is 0. We're starting the observation. So we set the time to 0. Speed is 0 because I'm holding it. It's not dropping. Position, we define or we choose to be 0. Now let's say, what would be the distance After 2 seconds, how much distance this object must have fallen after 2 seconds? What would be X? What would be X after 4 seconds? What would be X after 8 seconds? So on and so forth. And I can invert the problem and I can say, if an object drops from 100 meters height, okay, from 100 meters height, how long does it take? So if the height or the fall is 100 meters, what is the, how long does it take to reach or to hit the surface of Earth? Now, can we answer this question? Just looking at this? Well, we can answer this question by doing an experiment, by making an actual measurement, but that's not very practical, because if we have to answer this question every time, and every time we need very sophisticated instrumentation and experimental setup to make all those measurements, every time somebody asks a question and then answer these questions. It would be much more practical. And there are other quantities that you may want to know, or somebody wants to know. For example, if somebody wants to know what would be the velocity or speed, sorry, when this object hits the surface of Earth. Of course, the initial speed is 0, but what would be the speed when it is halfway through? Now, answering this is even more difficult than telling about X or time, because we don't usually, well, I'll talk about this, how we get the speed. Okay, so there is all these questions, well, we can answer doing an actual experiment, but that's not very practical. The most practical way is if we could find a mathematical description of this, a mathematical equation that we find, and then once we have the equation, then whatever our known variables are, we plug those known variables and we find the unknowns if we had a complete mathematical description. Any questions so far? The course outline, if it is not on LMS, I'll upload it today. It should be there already, and if it isn't, I would. Okay, any questions? Any other questions so far? Yes, Ali Safi. Please unmute and go ahead.
सर इसको हम लोग डायरेक्टली इक्वेशन ऑफ मोशंस जो हमने पढ़ी हुई है वो यूज करके नहीं निकाल सकते?
जी निकाल सकते हैं अगर आपने पढ़ी हुई है तो।
चलो ठीक है,
सही बात। बस वी आर ट्राइंग टू एक्सप्लेन द कॉन्सेप्ट ऑफ डेरिवेटिव। We're trying to learn the concept of derivative. I'm trying to introduce the necessity for those mathematical equations or the equations of motion, and how we arrive at them first before we start using them. Is it okay? Yes, there is. Yes, there is a formula. Yes, we were trying to get to that formula. Mohammed Hassan Bakar.
I'm sorry sir, मेरे derivative से unrelated question है, मैं उससे पूछ लूं?
जी पूछें।
Sir, recitations क्या चीज़ है?
जी रेसिटेशन ये 4 क्रेडिट आवर्स का कोर्स है, तो हम an hour and 15 minutes का एक लेक्चर होता है, तो this doesn't make up 4 credit hours of जो contact time है, so that's why we have recitations to make up for that. But usually the way we design is we teach new concepts in the lectures, like what we are doing right now. And then in recitations, we solve problems. We apply these concepts to problems. You will see this. We will see the first recitation on Friday and see what happens in the recitations. So they are part of actual lectures, actual learning. Any other questions?
Sir, thank you.
Any other questions? Yes, Moise Ilahi.
Sir, सर अब आप हमें टीच कर रहे होंगे ना, तो सर जो सर आदम ज़मान से हमारी ईमेल्स आ रही हैं वो हम इग्नोर करें?
देखें वो आदम से आपको ईमेल्स आ रही हैं हमारे सेक्शन में।
सर
कितनी
वो
ईमेल्स आई हैं?
एक ईमेल आई थी, उन्होंने कहा था कि वो एक उन्होंने बुक अपलोड की है LMS पे, वो हमने पढ़नी थी।
So the course content is identical, and so the exam would be the same, the quizzes would be the same, and we are co-teaching this course, Adam and myself. Adam is the lead instructor on this. So, and we are also we're cross-listed between us. So Adam is mindful whenever he sends, and whenever there is something of common interest, that's why Adam is sending you an email. So you don't ignore them, pay attention to them.
Okay,
So
sir.
they are as if I am sending to you. Okay.
Okay, sir. Thank you.
Okay, please lower your hands if your question has been answered. So we arrived at this point where we have just kind of learned the need for a mathematical model. All right, a mathematical equation, or what somebody has already called the equations of motion. We would formally learn equations of motion, but for the time being, I'm just trying to develop a mathematical model based on a physical phenomenon. So let's see. All right. So let's do an experiment, an actual experiment. And let's say we drop an object, we mark the wall, and we drop an object, let's say from 1,000 meters, and then we just, or if I could just 1,000 meters height, but let's say that this is the position, so it's 0, 40 meters, 80 meters, and so on. And we drop an actual object and we do an actual experiment. Okay, so we do an actual experiment and we drop an actual object, and we keep time, and we keep looking at the distance, and then we make a table of our observations. All right, so here in the first column, I record time, and in the second column, I record the position, which is initially 0, and so is time. So if you do an actual experiment in real life, this is what you would measure. I am saying it because I know the experiment and I know the equation behind it. That's why I can put these numbers on board. Otherwise, I wouldn't be able to do it. But you can imagine as if we are doing this experiment right now, and we are getting these numbers off the screen of our instrument. After 1 second, object of any weight drops exactly, if there is no air resistance, drops exactly 5 meters. After 2 seconds, the object drops 20 meters. After 3 seconds, the object drops 45 meters. And after 4 seconds, it drops 80 meters. After 5 seconds, it drops 125 meters. Now, based on, but we have enough point, I think, to make our discussion. So do you see any relationship between time and position? Can you guess one? In 1 second, it drops 5 meters. So it's 5 times the time. So the position is 5 times the time. In second case, it's 20. So that's 10 times the time. In third case, that's 15 times the time that it has dropped. And then in this case, it's 20 times. And in this case, it is 25 times. So it's not very easy. There is no apparent relationship. However, if you see that all these numbers, all these distances that the object has dropped or has fallen, they are divisible by 5. And let's see if I can write them. If I can write these numbers like this. Now, 5 is just constant in all of them. Look at the remaining number here, remaining part. Do you see a relationship? Anyone?
Perfect squares.
Yes. So this is nothing but square of the time. This is nothing but the square of time. If I can just make some room on the right side and rewrite it. So this is 5 times 1 squared. This is 5 times 2 squared. This is 5 times 3 squared. This is 5 times 4 squared. And this is 5 times 5 squared. And now this is time. Now looking at this table, can I write this equation that the position depends on time or the fall depends on time like this? 5 times square of the time it has been allowed to fall. Is this clear? There is a yes, no button somewhere in the non-verbal response. It would be really nice if few of you hit yes, and so that I realize that you're following. And hit
Yes,
no
sir,
if you're
it's
not
clear.
following. Hit no if you're not following. I mean, instead of typing it in chat, please use the non-verbal response. All right. So now we have arrived at a mathematical expression, and you see it relates time and position. And now, for example, we can answer all these questions or some of these questions on this other board, which let's see if I can bring it back. Technology. Oh, yes. So here, for example, now we have all these times that we wanted to answer. So we can plug now time here and find out how much distance the object has fallen, any object. I'm sorry, it's very difficult to go back and forth between boards. So let me just move on to the. While we are at it, let's learn something and something important as well here. Now we know the units of distance are meters. I have been writing them here. So X, the units are in meters. We also know that time is expressed in seconds. All right. and we have a square here. So we have a square on second as well. All right. Now, on this side, we have meters. On this side, we have seconds. What should be the units for a 5 for this equation to make sense? Okay, we don't
Meter
know.
per second.
Sir,
Meter per
the
second
way
square.
third.
So we don't know what quantity this is just yet, but we can look at the units here. So for this equation to make sense, for us to have meters on this side, it's very clear.
सर कैमरा ब्लर हुआ हुआ है
Sir, acceleration.
Sir,
S1S2.
Wait, one by one. Let me recognize you. Raise your hand if you make a comment. Don't speak. Don't over speak one on or the other. Okay. So now this, if this quantity has these units, the second square cancels, and then I have meter on both sides. All right. So now we know what 5 is. Well, I don't want to introduce it, what it physically means, but 5 has the units meter per second squared or second, if you, whichever way you like to say it. Now we have answered part of the questions that we ask. For example, we ask about how long an object takes for a given distance, or the other way around, how much distance it falls for a given time, and they are related through this equation. But what about the speed? I want to find out what is the speed of the object when it hits the surface of Earth. Now that question has not been answered. And to answer it, we need to first figure out a relationship between speed and this equation, or the quantities that we have at our disposal, the quantities that we are measuring, the time and the position. So now this is relatively simple. That if an object travels a certain amount of distance, let's say that an object has fallen 125 meters, all right? And the time it has taken to fall that much distance is 5 seconds, all right? So the speed would be 125 meters per divided by 5 seconds. So that would be 25 meter per second. So we can find speed through this simple relationship. But before I talk about speed, so I want to introduce a more symbolic definition. So when I say 125 meters distance, I am considering this distance between 2 points, a starting point and an end point. So if I denote my starting point with x1, and if I denote my end point as x2, so the distance between these 2 points can be symbolically written as x2 minus x1. Okay, whatever distance, let's say the object was falling from above, so it must have covered some distance before it reached here, and then it has covered this distance. Okay, so I'm not interested in the distance that it has covered before. We are just focusing in this interval. We're interested in this interval and the distance that it has covered in this interval. Okay, and to find out that distance, you take the final position and subtract the initial position, and then you get, so this is distance interval, and in the denominator you have time interval. So again, you may have started this experiment here. The object may have already fallen for some time, and at this point when we start this observation, let's say the time on the clock is t1, And at this point, when we stop the observation, the time on the clock is t2. So we divide the distance traveled by the time it has taken, and we define it like this. Okay. And this is how we can calculate speed. The problem is this, that this speed is not very useful, because this tells us the average speed of the object. It does not tell us the speed when it hits the surface of Earth. It does not tell us the speed here in the middle. Okay? It only tells us, it takes the total distance, divides it with the total time. Now, let me give you an example. Let's say you're driving from home to Lums, and when you start, you look at your car's odometer, or so you look at your car's meter, and you note down the distance. And then you look at your watch and you note down time. You get to Lums, and then you note both quantities again. And you do this calculation, and this would give you your average speed. Now, in between your home and Lums, you may have been traveling faster in some regions, depending on the traffic or the speed zone, and you may have been traveling slower. So this does not give us instantaneous speed. If you want to find out instantaneous speed at this moment, or speed at this moment, this definition is not very useful. That is why this is, let me just add the subscript. This is average speed. All right. Okay. So if you remember the table that we had in the previous slide, and if I can display that or make a graphical representation of that table, this is how it would look like. Now that we have established this relationship between x and time, right? What this means is that x depends on time. So I can write it in a more symbolic way. X of t, this reads as x of t, and it signifies that x is a function of time. X depends on time. The two variables, x and t. And when two variables are related in this fashion, usually this variable is called or regarded as independent variable. This variable on this side is regarded as dependent variable. And whenever you graph two variables, you always keep the independent variable on this axis, on horizontal axis, and the dependent variable on the vertical axis. Okay, so we have time here. And we have position here. All right. Now, if I put all those points, this one at 5, next one at 20, this one has 45, 80, and 125. Okay, so this is how the graph looks like. I apologize for my drawing. This is a quadratic curve. Should look like a quadratic curve, but it doesn't on the, I'm sorry for that. Okay, so this is the graph, and what average speed does is it takes one point on this graph and another point on this graph, okay? And then it takes the interval in time, and I can write the interval in time. I can define a new variable, and let's say t2 minus t1. This indicates an interval in time, and there is a short way to write it like delta t. These are not two variables. Delta t indicates one variable, a time interval. Okay, and so is the case for x. x2 minus x1. This is an interval in space or distance, and a distance between 2 points can be denoted as delta x. Okay, so it has delta x, and on this side we have delta t. On this side we have delta x, and you can read it from the x's. So this would be delta x, and this would be delta t. All right, and the average speed is the gradient of a straight line between these 2 points. Graphically, if you want to know, the average speed V average is x2 minus x1, t2 minus t1. It is the gradient of the line joining these 2 points. Okay. Now, before I move on, if you're just looking at this curve and you want to find out the instantaneous velocity, that the average velocity cannot tell us, something that we want to know, what is the instantaneous speed of an object at any point in time. Let me first define it graphically, and then we will define it mathematically. Right? So, but before I do that, let me quickly say, for those who are not familiar with this concept, that if you have a curve, any curve, f of x as a function of x, any curve like this, okay, any curve, a line that touches this curve at only one point, a line that touches this curve at only at one point is called tangent of that curve at that point. Of course, if a line touches this curve here, it would look like this at one point. If this line touches this curve at this point, then it would look like, you see that this tangent at different points has a different inclination, has a different gradient. So that is what a tangent is, okay? And the instantaneous speed on position and time graph is nothing but tangent to this curve at that point, at that instant. This is the instant, one single point in time, notice. And I want to find the velocity at that given point. Graphically, the tangent to this curve, sorry, the gradient of tangent to this curve is what the instantaneous speed is. All right. Any questions so far? So I have Ahmad Umar. Yes, please. All right. So no questions. Okay. So this is the instantaneous speed on the position time graph. This is a graphical definition. But now I want you to see something else. And this is the most important part of this lecture, I think. That if I start reducing, and here is my definition of the average speed. Let me write it one more time. Delta x over delta t, right? Now see this, look at this blue straight line. That gives me the average speed where we have delta x and delta x divided by delta t. Now, if I start reducing this delta x in such a way that, let's say that I chose this point to be exactly in the middle of delta t, okay? Exactly in the middle of this interval, that this interval is delta t, and my instantaneous speed position is exactly in the middle of this. Okay, now if I start reducing this delta t from both sides, what would happen? The delta x would start shrinking as well. So these 2 points would start moving on the curve from both sides towards this point. And if I can, and you can mathematically, if I can make this delta t infinitesimally small, it's a new word if you haven't heard it, something very, very small. If I can make this delta t very, very small, the delta x would, by dependence on t, would become very, very small as well. And these 2 points would coincide with this. And now the tangent to the curve would become, now this average speed would become instantaneous speed in the limit where delta t is very, very small. So if and I'm introducing the concept of limit here. If I take, and this is how we represent mathematically taking limit delta t going to 0, okay? Delta 2 so small as it almost 0, not 0. Then limit delta t 0 delta x delta t. And then this becomes, there is another mathematical notation. When we have a infinitesimally small intervals, these are non-infinitesimally small intervals, delta t and delta x. But when we have very, very small intervals, we usually denote them as dx and dt. Now this dx and dt is both, physically, it's the instantaneous velocity. Graphically, it is the tangent to the position time graph. And in terms of calculus, this is nothing but the derivative. Any questions? Ariba?
आप प्लीज ये लिमिट वाला कॉन्सेप्ट रिपीट कर सकते हैं?
जी जी बिल्कुल.
थैंक यू सर.
अरीबा, आपको ये समझ आ गई कि ये 2 लाइन्स हैं. This line is touching the curve only at one point and it is tangent to this curve. Okay, and graphically, as I said, that the gradient of this curve, this line tangent to the curve is the instantaneous velocity, and the gradient of this line, the blue line, is the average velocity. But if I start reducing, making this delta t smaller and smaller, okay, the delta x would become smaller and smaller. You see that it decreases quadratically with t. See, if I make t smaller, the x would become quadratically smaller. At some point, if I make delta t so small, okay, that it reaches both points from this side and this side, because this interval is shrinking, that they coincide, okay? And that is what limit is, making something infinitesimally small. So if I take the limit of V average, if I take the limit of delta X over delta T, what I'm getting to is the instantaneous velocity. What was previously average velocity between 2 points, you see they are different positions, these 2 points, but this is at one position. So only one point at one time. So if I take the limit delta t to 0, I get the instantaneous velocity. Okay, and that is also the definition of a derivative. The gradient of a tangent to a curve is the derivative of that curve at that point. So curve in this case is x of t, and this red line here, or the pink line here, is a tangent to this curve. And if I can calculate the gradient of this line, the gradient, that would be the derivative, and we read it dx over dt, or you can also call it derivative of x with respect to time, while x has to be a function of time for this concept to stand. And we know in our particular case that x does depend on time. X is a function of time. Is this a bit clearer than before, Ariba? Arslan?
अस्सलाम वालेकुम सर ये जो आपने लास्ट लाइन में लिखा हुआ है v average equals limit as delta approaches 0, ये v average की जगह सब्स्क्रिप्ट में v instantaneous velocity नहीं होना चाहिए?
नहीं, वो तो बाद में आएगा ना, जब लिमिट एवेल्युएट कर लेंगे, वो यहाँ आएगा, ये आ जाएगा जब लिमिट एवेल्युएट कर लेंगे। तो ये dx over dt is v instantaneous, not this one। ठीक है,
तो ये जो एक्सप्रेशन है ये instantaneous।
हाँ देखिए ना, ये सारी v instantaneous है। Limit of v average is v instantaneous, okay? ये सारी v instantaneous है, और जब मैंने इसको simplify कर दिया, then I've written it v instantaneous. But this is not v instantaneous. You can't take the limit because that limit has already, in this case, the time is already infinitesimally small. The limit has been taken.
Understood, sir.
जी राफे,
सर
Please.
वो मैंने बस ये पूछना था सर, ये लिमिट का जो वेरिएबल है, मतलब ये सिंबल, ये पहली दफा देखा है मैंने, तो इट्स लाइक विल वी हैव टू नो कि क्या करता है ये, मतलब ये कैलकुलेटर में होता है, क्या सीन होता है, जस्ट इज इट जस्ट देयर फॉर द अंडरस्टैंडिंग पर्पसेस?
नहीं, आई डोंट नो, मुझे पता नहीं है मॉडर्न कैलकुलेटर्स का कि उनमें होता है कि नहीं होता, बट analytically we would learn a bit more how to operate limit. Okay, we would have more examples.
Thanks, sir. Thanks,
more
sir.
functions. Umar, quickly.
सर आपने कहा था कि ये जो अगर हम लोग लिमिट को नियरली जीरो की तरफ करें तो हमें इंस्टेंटेनियस वेलोसिटी मिल जाएगी, किस तरह?
देखें, इंस्टेंटेनियस वेलोसिटी और एवरेज वेलोसिटी में क्या फर्क है, उमर बताएं आप।
एवरेज होती है नॉर्मली पूरे पाथ की, और इंस्टेंटेनियस होती है एक पॉइंट पे।
बिल्कुल ठीक है। तो अब देखें, मैंने यहाँ ग्राफिकली ये ब्लू जो ये चाक से लगी हुई है लाइन, ये दिखाया, ये एवरेज वेलोसिटी है। ठीक है, इतना बड़ा डिस्टेंस है टाइम में। ठीक है, इतना बड़ा डिस्टेंस इसने कवर किया, इंटरवल कवर किया पोजीशन में। ठीक है, इनकी जो रेशियो है दैट गिव्स मी एन एवरेज वेलोसिटी। ठीक है, अब इंस्टेंटेनियस वेलोसिटी एक पॉइंट पे होती है, उसकी मैंने ग्राफिकल एक डेफिनेशन बताई है कि ये जिस पॉइंट पे, आपने खुद ही कहा है ना कि वो एक पॉइंट पे होती है। ठीक है, तो ये मैंने एक पॉइंट ले लिया, आई वांट टू फाइंड आउट वेलोसिटी एट दिस पॉइंट। तो उसकी ग्राफिकल डेफिनेशन ये है कि इफ यू ड्रॉ अ लाइन दैट टचेस दिस कर्व, ये जो मैंने पिंक लाइन बनाई हुई, आई डोंट नो इफ द कलर इज विजिबल इन द वीडियो, तो दिस the gradient of this line gives me the instantaneous velocity. And if I take the limit on this blue interval and make delta t so small on both sides, the interval shrink towards this point, then what I would have is mathematically or geometrically the gradient of this red line, but physically I would have calculated the instantaneous velocity at this point because I defined it before this way. जी राफे।
सर माय बैड, मैंने हाथ नीचे नहीं किया था।
कोई बात नहीं, ठीक है। All right, so this is the graphical definition. So now let me introduce a more symbolic and formal definition of a derivative. All right. So here I have x and a curve f of x. Let's say that this curve looks like this. Okay. Now derivative is always defined as graphically, that if I draw a tangent to this curve, a tangent to this curve, the gradient of this tangent, which is here, delta x, and on this side I have delta f. If I may write, I will elaborate what delta f is. Okay, so now this gradient of this line, and I should drop this more. Right. Now this is a formal definition of a derivative. If I have a situation like this, the gradient is defined as f of x plus delta x, right? This value of the function. Let's say that at x plus delta x minus f of x over. So this f of x plus delta x denotes this point here. F of x denotes this point here. Okay. And this is f of x. Similarly, this is x on x-axis, and this is x plus delta x. So I have x here, and then I have x plus delta x here. Now you know the geometrical definition of slope or gradient, that you take the difference of these two points and divide it with the difference of these 2 points. So x plus delta x minus x. Okay, this is slope of the tangent to this curve at this point. I can also use the symbols that I used before. You can write this is the ratio of delta f over delta x, and this is okay, the same thing. And now if I take limit delta x going to 0 for this, okay, and on this side, well, I can already simplify this. X cancels this x. Okay, limit delta x And this I can write in the short form as df over dx. On this side, I still have limit delta x to 0, f of x plus delta x minus f of x over delta x. So this is the ab initio definition of derivative. What I mean by ab initio is the first principles. This is the fundamental definition of a derivative. This is the derivative of this curve f or this function with respect to x at this point. Okay, this is the definition of derivative, and we would apply it to calculate a few derivatives. To make it more clear, but to make sense of what good is derivative? Well, the derivative of position with respect to time gives you what?
Rate of change.
Rate of change of what? Rate of change of displacement with
Speed.
respect to
Velocity.
time. So what that is? Speed.
Velocity.
If we ignore that, if let's not introduce velocity just yet. So we're considering distance and time. So the derivative of x with respect to time is velocity. Okay, so derivative is useful. It gives, we can calculate physical quantities. Okay, any question? Okay, let's finish and then I'll take the questions at the end, because there's just 5 more minutes, I guess I have. Okay, let's consider a function and take its derivative. So you have the definition, all of you. Df over dx is equal to limit delta x going to 0, f of x plus delta x minus x. Let's apply it to some function. I have to erase because I can't switch boards as quickly. So I'd use this space here. So let's take an actual function. F of x is equal to x squared. Okay. Now we would calculate the derivative of this function using first principles, or using this definition. Df over dx. I know you know the shorter way, some of you, but don't worry about that. We would learn that and we would use that as a more practical way, but to introduce the concept, I'm going to use this definition to calculate this derivative. Okay, so limit delta x going to 0. Now, this would be the function definition, x plus delta x squared. Remember the definition, x plus delta x squared. See this? This is my f of x plus delta x. This would be simple f of x. That is x squared divided by delta x. All right. So now let's simplify this expression. Open this square, x squared plus 2 delta x x. So let me just write it in the other order so that you don't confuse. X delta x minus x squared over delta x. Okay. Now,
आपने delta x square miss कर दिया, I guess.
yes.
Delta square.
Thank you. Delta x squared minus x squared. Now this cancels. All right. And then I can take the delta x common. 2x plus delta x divided by delta x. Now this delta x cancels with this one, and then I impose the limit, then I evaluate the limit. So delta x is limit delta x going to 0. That means delta x is negligible. I just ignore this as well because of the limit. And that's what when I have evaluated the limit, and my answer is 2x. So that is the derivative of the function f of x equal to x squared, and the derivative is 2x. The derivative of this
So
is
why did
2x.
you cancel the delta x in the bracket?
Because it's very small. Delta x limit is going to 0. I've evaluated the limit. Okay, I just ignored it. All right. So I'm going to erase this because I want to use the same space again. And one more last example.
Sir,
then-
why did you write it as x plus delta x square instead of f of x plus delta x square?
Because that's the definition of the function, right? This is my function. This is general. We don't know what the function looks like. Here I have specified what the function looks like. It's x squared. So I have to plug the value of x plus delta x here in the argument, and that is it's squared. So that's why x plus delta x is squared. But thank you for asking this question. This point could be confusing.
Thank you.
Very good question. Okay. Okay. Next.
Excuse me, sir, can I ask the question?
Yes, yes, yes. Sorry for erasing this if it was about this. So
नहीं सर कोई मसला नहीं तो सर इसमें हमने लिमिट वाले मेथड से we got to the derivative but previously in A levels वगैरह we used to just use the normal rule for differentiation and get to the answer directly. So are we supposed to go with this method in this course?
you're supposed to know both methods, and you're supposed to go with both whatever method is required by the circumstances. So I can't say one over the other. That's more practical, more fast. So in actual life, in real life, you use those rules, shorthands, and we will learn those rules as well in next lecture. Okay, but to understand it, this is where this is the definition. That's why it's called derivative by ab initio. So if in an exam or in an assignment you read, find out the derivative of this function ab initio using the ab initio method or the first principles method, then you must use this approach. Okay, if you're just asked to evaluate a derivative, then use the shorthand, the short rules. And if you're solving another problem which is not about the derivatives, but it requires the calculation of the derivative, use the shortest method, the quickest, and the one you can do better. Okay, so let me just very quickly bring back our hard worked mathematical model. X of t equal to ct squared. And now by definition, I can calculate its derivative, dx of dt. Okay, and we already know that that would be speed. Okay, so that would be the instantaneous speed. So if once we know this relationship, which we developed today earlier, we can calculate that not just the average speed, but instantaneous speed. And that is just the derivative. And I leave this for you as an exercise to do it first principles. I'm just going to write the answer here. 2ct. This is the answer. Interestingly, now you see that the instantaneous velocity also depends on time. That's why when you drop an object, it falls faster and faster. It falls faster and faster because the velocity or the speed of a free falling object depends on time. So the more time passes, the more speed the object has. It goes faster and faster. Sorry, if we know the direct method, do we have to use the, when explicitly said to do it, then do ab initio, otherwise you can use the direct method. Okay, so the speed of a free falling object depends on time. It's a function of time, and I can take another derivative. Now, v is a function of time. This is what we have here, the instantaneous. And I can take another derivative now of v with respect to time. Okay, and that would give me 2c. Again, I'm not using the first principles ab initio definition, but please do this using ab initio at home. This is an exercise. And now this quantity is my acceleration. Okay, the derivative of velocity with respect to time of the velocity time curve is acceleration. And since this is a free fall example, this a would be actually g. Okay? And its value is approximately 10 meters per second squared. A more precise value is, I think, 9.8 meters per second squared. But the acceleration is constant. You see, it does not depend. Now, acceleration in this expression does not depend on time. And that is what Galileo observed in the 17th century. He found out that freely falling objects fall at the same rate. This constant I just introduced at some point. Oh, sorry, I forgot to say. This c is actually 5. Remember the constant that we, remember the value that we used in the model when we drove? So that's why a c is there. But you could just play with, you can plug just 5 here, or plug the value of 5 here, and you will get 10 meters per second. Okay, so but this is, so now look at this. This is what Galileo found, that the rate of fall or the acceleration for heavier or lighter objects is constant. It does not depend on time. It does not depend on how heavy an object is. And you see how different quantities are related to each other. And one last thing, for example, here I have dv over dt, which is equal to acceleration. Okay, but v itself is dx over dt. I can combine these two in this fashion, d over dt, and then plug in the derivative definition of velocity, dx over dt. See this? This is called double derivative. Okay? And in short form, you could write it d squared x over dt squared. So if you want to find acceleration from the position time curve and are not interested in velocity, you can just directly take the double derivative of this curve and find out the acceleration. Okay, and that's all for today. Thank you very much for your attention. I'll be happy to answer your questions now.
सर वो अभी तक वो समझ नहीं आई, वो जो आपने x प्लस डेल्टा x स्क्वायर जो किया था, होल स्क्वायर जो किया था, वो